Okay, so let me talk now about the symplectic implementation of all this and the doubling that makes sense for any symplectic manifold. Before I do that, let me just say so two comments. One comment I forgot to make, which was that I talked about the Ustinov branes, which are somehow the prehistory of the generalized complex branes. And when you saw how I wrote the data looks very similar. Unfortunately, the precise dictionary between Ustinov branes and GC branes is not quite worked out. So the data looks very similar, but it's not quite the same. And so it still requires some work which needs to be carried out. There is some confusion, at least that I have, and in this time to sort it out, because in one of the contexts, the fields appear as symmetries, and in the other context appears as data. So there is some normalization that one needs to do in order to compare. But I'm going to talk about the GC branes now. The other comment is that apparently I missed some signs in the examples when I wrote the symplectic structure as a GC structure and the complex structure as a GC structure. There has to be a minus sign in one of the entities in the matrix. That's too much detail. Okay, so what is this factor doubling? So the Kaehler GC manifold, say J H is a GC structure on X. Well, you can write J as a block matrix. It has an I, this is IP, IP check. Then there's a coefficient P here and a coefficient Q here. And P is a bivector and Q is a two-form. And part of the integrability condition of the GC brane, the GC structure can be recorded by saying that P is not just a bivector, but P is a Poisson structure. Close with respect to the Neuhaus structure. So let's do this part of the GC structure. So a part of an integrable GC structure is really a Poisson structure. So let's zoom on that. So consider now only X and P. And the first the first remark, which is somehow the starting point of this whole translation, is that every Poisson structure has an interpretation in terms of as a shifted symplectic structure. So one shifted symplectic structure. So for some geometry, it's really symplectic geometry in disguise. You just need to sacrifice something. What you need to sacrifice is that you're working with slightly fuzzier spaces than manifolds. Okay, so let me try to explain that. So let me just recall the notion of the real algebra. I already mentioned the algebra a bunch of times, but let me now remind you what that is. So real algebra on a manifold X is the data E together with the map to the tangent bundle of X, and then some bracket E. So E is a vector bundle. A is a map of logarithmic sheets. This guy is a Lie bracket on E, R linear on E, and their conditions. So this A is called the anchor map. It's a map of sheets of the algebras. And it also satisfies the limit. So if you take two sections, say S and T in E, and you multiply one of them by a function, and take the bracket of that, well, first there is a linear term where F multiplies the bracket of S and T, and then there is a derivation term which says that you need to take the Lie bracket of the anchor of S acting from F and multiply that by T. So this is A, and the bracket satisfies this. And now the remark is that every Poisson structure is not destroyed. Where the bundle of the algebraic is the tangent bundle, the map is given by the Poisson structure, and the bracket on the tangent bundle is given by the Poisson structure again. So we get my science guide. So this is you contract so you contract alpha with T, that gives you a vector field, you redifferentiate beta like that, then you subtract the same thing the other way around, and then do plus or minus. You take the derived differential of the bracket of the contraction of alpha and beta. So this gives a little algebraic. It's called the Poisson corresponding. And now the thing to do is you think about post-algebraic as affiliation, or sorry, algebraic manifold. Think about this affiliation. So given algebraic, this is a special case of what's called a derived affiliation. So there is in derived geometry, derived algebraic geometry, there is a whole theory of these derived affiliations, which essentially are maps from differential graded Lie algebras, shifting differential graded Lie algebras, or infinity algebras to the tangent bundle, satisfying all these conditions. And they generalize and in fact resolve and refine the ordinary notion of affiliation and the ordinary notion of singular affiliations. So if you have a little drawing, it gives you an example of one of those, and you can use this the derived algebraic geometry machinery to actually quantify by derived affiliations. So, the key fact is that quotient spaces, infinity spaces or analytic spaces or algebraic spaces by derived affiliations exist always as formal spaces in the same algebra. So you can't quite make sense of them. They can be correlated on Falstaff and messy, but they're spaces. So you can't quite make sense of them as spaces with good functional theory, but you can make sense of them as spaces with good formal function, with no conversions. And so in particular, if you have an algebraic in form of quotient, X is a manifold, C infinity manifold, and T is an algebraic. We can form this quotient by this affiliation. In brackets, because this is actually a formal C infinity stack. So there is a model for that locally looks like a manifold quotient by non-embedded equivalence relation, which is given by the formal power series of manifolds sitting in another. So this always exists, and now, well, the shifted guys. So if you have a Poisson algebraic, then the quotient, I'm call it script X, so it's a formal C infinity star. This star is actually formal C infinity smooth star, which has one shifted symplectic star. Right, on the X, and is such that the natural quotient map from X to the script X is Lagrangian for that one sheet. In fact, this is actually a structure again. Let me explain this quickly. So where is that coming? What are we talking about? So if you have an algebraic derived star, it works for C infinity, but I'm just going to say in the algebraic context, or an analytic derived star, which is what's called locally affine representation. And it's some technical condition which is always going to be satisfied. So this is the analog of smoothness. Then because it's derived and because it's stuck, it doesn't have a tangent bundle, but it has a tangent complex. And in fact, this locally affine representation condition is equivalent to the condition that this complex is a complex, finite complex of vector. So this is the analog of the statement in algebraic geometry that say a variety of the complex numbers is smooth if its tangent sheet is a vector. So it has a tangent complex, but it's complex. So it has terms in various degrees. And so there is a notion of there is a notion of closed bonds. And shifted T-forms. So there are closed T-forms on X shifted by N. And the way you describe those is you say you take the cotangent complex. So these are elements in degree T cocycles of shifts. So you need to take the fifth step of the Koch filtration on the cotangent complex. Segment.
correctly. So for every test space, if this is derived say scheme, and we have a map from S to X, then the pullbacks. So if you try to test what the forms are on that guy, these are degree key cocycles in the total complex. You need to take it with respect to the product of the pit step of the Koch filtration of the RAM complex of S, and I'm going to mess my I think it's plus and shifted by n. There's some shifts. Which I haven't written for, so these are suspect. But the point is that you take the double complex, which is the pit step of the Koch filtration of the tangent complex of S, and you take a cocycle of degree P, but maybe with some shift. And so concretely, if you take, so I think these shifts are written. If you take a form and you pull it back, the test space, it's going to be a sequence of sections in the terms of the cotangent complex. Where this omega I is in the P plus I and N minus I piece of the cotangent complex. So this is, so what I'm doing is I'm taking the P forms on S. So these are just, it's a complex, which is the pith power of the cotangent complex of S. And it has terms, and I've labeled those terms as omega P comma K. So you get all these pieces, and it's just the cosine condition is just the cosine condition for the double complex. So these have to be such that the RAM differential of the form omega I is minus the inner differential of the form I plus 1. So it's a cocycle in the total complex of the double complex. It has many terms. In fact, it could have infinitely many terms. Of course, you know, if all the terms except for the first one are 0, the first one is a section. It's just a P form, right? It's a section in omega P 0. And if all of the other terms are 0, it just says that it's closed with respect to the RAM differential. But in general, you know, you could have these other terms that are implementing the closure. The first term is not closed, but then there are higher terms that close it. So these higher terms are called the key, closing the form, closing the underlying T form omega 0. So these closed T forms or shifted T forms, they are they're T forms, shift T forms or shifted T forms, but the date of closing them is extra data because it's a co-cycle data in this context. And in fact, this data that close the forms may be non-trivial. They give you a space which may be not contractible. And so a symplectic form on a derived stack is a closed two form. And shifted symplectic form on X is a closed and shifted two form omega, such that the reduced map for the underlying form, or contraction with omega going from the tangent complex to the cotangent complex shifted by n, it's an isomorphism in the sense of complexes, so it's a quasi-isomorphism. This of course, is in this picture that I described, is what we call omega 0. So, symplectic form is this data of the closure, it's two form, may be shifted, and then it's the data of the closure, so that it gives you an isomorphism between the tangent complex and the cotangent complex, but because those are complexes, group each other, and they have some terms which are not symmetric around 0, there is no chance that these guys have the same amplitude, the same terms, so they cannot be quasi-isomorphic, but up to a shift you can, because they're complexes of the same length, up to a shift you can put them in the same degrees and then they can be quasi-isomorphic. So that's why you make this shifted notion of a form. Because normal symplectic forms may not exist, but shifted ones have a chance of existing. Now, how is that relevant to the Poisson story? So if X is Poisson, then you have this derived foliation, this algebraic. And then X is the formal stack. And what is the tangent complex of that X? Well, it is the algebraic if you pull it back to X. So if Q is the natural map from X to the script X, then the tangent complex of the script X is just this complex, EX dual mapping to TX with P, where this sits in degree 0, this sits in degree -4. Now the dual complex, so the pullback of the tangent complex is the dual of that. So this, the dual of Tx is Tx dual, the dual of Tx dual is Tx. The map is the dual of T, that is a Poisson structure, so it's again T. And this sits in degree 0 and this sits in degree 4. And so if you shift the cotangent complex by 1, we're just shifting the whole thing to the left. So this is now sitting in degree -1 and this is sitting in degree 0. By the rules of the shifting, we need to put a sign there. So it is essentially the tangent complex, with the only difference being this is a minus of the map. And now it's quite clear that we can write an isomorphism between those two. With omega 0. So it takes the complex Tx dual goes to Tx and maps it to the complex Tx dual goes to Tx, the map minus P. And remember, this is sitting in degree -1, this is sitting in degree 0. And it's clear that, so you put the bottom map to be the identity and the top map to be minus. So that gives you a quasi-isomorphism. In fact, in this case, it's an actual isomorphism of complexes. And one can check that there is a one-shifted symplectic structure in which the key is trivial. This is closed for the derived differential. Omega 0, 0, 0, 0, 0, which is the pullback that you this kind. Also, there is a Lagrangian structure. On the map from X to X. I'm not going to describe it. So Lagrangian structure in this case, it's a homotopy between the pullback of the symplectic structure by Q and 0. So it's extra data. And in this case, the homotopy is again P. And then there's a non-degeneracy condition there. But there is a Lagrangian structure, which is entirely given by P. So I'm going to say gamma Q, which is really equal to P. You know, it's a homotopy between this map and 0, which is going this way. So the punchline is that if you have a Poisson manifold, you get a formal stack, which is the quotient of the manifold by the cotangent bundle, by the Poisson structure. And on it, you get a one-shifted symplectic structure and Lagrangian structure on the quotient. And in fact, this is an equivalence of spacing. So this gives map Poisson structures T on X to X, which is X on the dual X form stack omega X one-shifted symplectic structure and gamma Q Lagrangian structure on X going to this big. And so as I said, this map is actually an equivalence. But there is a theorem which is due to Costello and Rosenblum, And what it says is that the space, the modular space, or the groupoid, if you want, Poisson structures on X is weakly equivalent to the space Lagrangian maps from X to X prime, where X prime is a formal one shifted symplectic stuff. So this actually realizes this long-term program of Alan Weinstein of understanding Poisson structures in terms of symplectic groupoids. And this is what the statement really is. So the one caveat here in this statement is that you need to say Poisson structures are just Poisson structures up to Morita equivalence. But you need to say what the equivalence of the Lagrangian maps is. And the equivalence of the Lagrangian maps is up to a tau localization. So two Lagrangian maps, X to X prime, and X to X double prime are equivalent if there exists a Lagrangian map X to Z. So this is formal and one shifted symplectic. So that we have a factorization, primitive diagram. So we have X mapping to X prime, mapping to X double prime, and Z maps to both of these. And A prime and A double prime are a tau. Meaning they induce an endomorphism of tangent points. They're formally a tau and compatible with symplectic structure. So once we introduce this equivalence of the Lagrangian structure, then you get full diction between Poisson structures and these one-shifted symplectic stacks together with Lagrangian units. Okay, now back to the GC structures. I only focus on one piece of the GC structure, which is the Poisson structure. But the GC structure, remember, had I, P, Q, and IT check. And so the almost complex structure condition it is really 4 equations. It says that IT squared plus QP is minus 1T. IT check squared plus PQ is minus 1 on T check. And then there are two more conditions. P intertwines IT and IT check. And it also intertwines, Q intertwines IT and IT check. So the way you want to interpret this is to say, that so you have the tangent complex of X, the portion stack pull back to X. Remember, this was just the algebraic complex. And you can say that I and I check give you an endomorphism of this tangent complex. Where here you have I check, and here you have I. So the diagonal part of the so the P gave us the portion stack, which was one-shifted symplectic with the Lagrangian map. The diagonal part of the GC structure just gives you an endomorphism of the tangent complex of this stack. Right, this condition just says that that's a map of complexes. These two conditions say that this map, we'll give it a name. Maybe I should call this straight J. So this J, so equation 3 says that J is a map of complexes, and equations 1 and 2 say that J squared is not quite equal to minus the identity, but it's homotopic to minus the identity of the Q. And this last equation says something about compatibility of this homotopy with IT and IT check. So the moral of the story is that the data of a complex, of a generalized complex structure can be rewritten as an almost complex structure on the quotient guy, which is almost complex up to a homotopy correction. So it's not literally equal to minus the identity, but it's equal to minus the identity up to homotopy. And so the first proposition that we check is to say that a GC structure on X defines a weak or homotopy complex structure called J X on X, which is integrable. And homomorphic one-shifted symplectic form. Next, with respect to that structure. And okay, let me just say, so what's the relationship between this guy and homomorphic? Let's call it omega homomorphic X. What's the relationship between this guy and what we had before? So there is an omega 0 homomorphic, omega 1 homomorphic, and other stuff. The omega 0 homomorphic is what we had before, which is omega 0 minus plus I times J, and omega 1 homomorphic is I times H. And the upshot is that if you just take the Poisson piece of the GC structure, you get a stack which is real stack, formal stack which is one-shifted symplectic with a Lagrangian structure. But if you take the rest of the GC structure, this real stack is the complex structure, because it's a stack, it's only weakly defined up to homotopy. It's integrable, again, only in the weak sense. The real symplectic structure becomes the real part of a homomorphic symplectic structure, which is one-shifted again. And our X is Lagrangian of the real part. And let me just make a remark to say that this is not obvious statement, because I cheated a little bit. I wrote everything on the pullback under Q rather than on the actual stack. But the function theory of the stack is given by the Chevalier-Eilenberg complex of the algebroid. The functions on X are the Chevalier-Eilenberg complex of the algebroid. So if you want to really write everything downstairs rather than pull back, you really need to write it on the pullback, but linear under the action of the Chevalier-Eilenberg complex. Which means that what I've written here are symbols of some polydifferential operators. We need to list those symbols of polydifferential operators. So if we literally want would try to prove this in a strict model on the given complex without doing any replacements up to homotopy and up to cofibron powers, then I've done very little. I've written only equations, algebraic equations on symbols on polydifferential operators. You actually have to write the acts of polydifferential operators. We must leave this to polydifferential operators. And this is not how we do it. We actually write it in the in some cofibrant weak models by using foliations. it's a priori not clear that the strict model even exists. But actually, in the power through this, and he actually could prove that this does exist. So they're explicit formulas. For everything, for the complex structure, for the homomorphic form, and for the Lagrangian structure. You gamma cubed directly in the strict model for the cotangent complex in terms of point operation. And in particular, once he has formulas, he can prove this theorem directly. So he's gave the proposition. So this is just a different proof, in some sense, much more concrete and satisfying than what we have. So, you know, do I have 4 minutes?
That's fine. Because we started 5 minutes later.
Oh, okay. So rather than telling you, okay, so there is a maybe let me say this in 3 minutes and then I'll say something else. So there is a version of this for the GC branes. So the brane version is to say that so remember what we said is that GC structure on X are the same thing as one shifted homomorphic homotopy complex structure on script X, one shifted homomorphic symplectic form omega homomorphic X and a Lagrangian structure on this totally real guy. So the straight X maps to the strict X as a totally real submanifold. Happens to be Lagrangian. For the real part of the homomorphic symplectic. All these gamma cubes. And GC branes in a given GC structure they will correspond to at least in the weak setting here. they'll correspond to a homotopy complex structure. So you know the given GC structure is given. So this X with its homomorphic structure, omega homomorphic, and the Lagrangian structure are given, and this will be a homomorphic stacks script Y mapping to X, Lagrangian structure let's call this I mean maybe F because it's not necessarily an embedding. Lagrangian structure gamma F with respect to the homomorphic symplectic form. And one more piece, which is a Lagrangian structure let's call it gamma X. Let's call it gamma on the intersection of the script Y with the straight X over the script X with respect to the induced symplectic form. So I didn't explain this, but in this shifted symplectic geometry, one very powerful thing is that if you have two Lagrangians and you intersect them, on the intersection you have a symplectic form of shift one less. So this GC branes, the GC geometry is just encoded in some symplectic geometry and some Lagrangian structure, and the GC branes are just other Lagrangians together with Lagrangians in the Lagrangian set. So and we don't quite have the strict version of that, right? So the English theorem gives us the strict version of that, but the strict version doesn't quite work here. So I don't know what's going on. So maybe I don't have time to do that, but what's more interesting is that beyond this generalized complex geometry, we can also do generalized Kaehler geometry this way and do topological twists of sigma models. But beyond the generalized complex geometry, you can actually study this theory of integrable homotopy complex structures on derived stacks. And there is a very good theory of those, and there is a new one, the derived, which shows you that every integrable homotopy complex structure on a real derived stack comes from a homotopy complex structure on a complex stack. It's exactly like the ordinary new one, the derived. But so it works in exactly the same way. Just the proofs are much harder, and they require actually the development of some quite interesting theory of deformation theory and Galois theory of complex structures. In fact, one can do it for any change of fields. There is some Galois descent for these integrable structures of the homotopy. I mean, there's a whole analog of these for paracomplex structures, which you can actually write over arbitrary fields, arbitrary finite field extensions. And it all works, and it's the same theory, but it requires some machinery to be developed, and that's what we're doing. We're finishing that now. Okay, sorry, I'm going to stop.